things. I'm out here. Okay, so we're back for part two of the discussion. Andy and Robert are back. I don't remember exactly where we left off. I know that Robert wanted to talk about the oil drop experiment, Millikan. It's probably like the 10th time or so that he's wanted to talk about it, but that's fine. It's probably important. So, Robert, why don't you start today, and then I'll chime in a little bit later with what I'm working on.
In relation to the last video, it's a question of understanding this experiment correctly. Millikan did his experiment during the year 1909, publishing his results in 1910, if memory serves. And in the process, they measured the electric negative charge of the electron in Coulomb value. And because of the experiment setup, they were able to measure a positive electric charge, which was assumed to be the value of the proton electric charge. The problem with that experiment was an understanding in its design. There was an error. And the error was due to not understanding how electrons behaved. So the experiment had a grating, a mesh, through which oil droplets from a perfume bottle were expressed. That grating was negatively charged. So electrons, as we now know, are free to move, and the oil drop gained electrons in addition to what was already there, and hence expressed a negative electric charge. Then using gravity measures as well as electrical field measures, you're able to determine from the speed at which the oil drop either descended or ascended what sort of electric charge was on the oil drop. When they changed the field polarity of the grate to positive, electrons would migrate from the oil drop to the grate, and the drop would gain an electric charge that was apparent positive. The problem with the experiment is that they missed what was going on. What they were measuring was the addition of electrons or the removal of electrons, and never ever at any point in this process did they ever measure the electric charge due to a proton. At the time, there was another guy in Austria called Endraft who performed similar experiments, except he used water droplets and produced a different set of charge values. And he criticised quite strongly Millikan's claims, where Endraft said Millikan should have published all his results and not just relied on the good ones or whatever. And there's been a fairly heavy debate at the time and since, and then Millikan's original lab notebooks became available, and the controversy reignited about whether Millikan had been fair in publishing his results. But the end result was Millikan got a Nobel Prize for determining the electric charge. But the mistake that's been made and carried on for now 112 years, 114 years, is that they've never measured the electric charge of the proton. And the experiment has that design flaw in it that's not been realised or acknowledged. And as a result, in 2015, I made a claim that the electric charge of the proton could not equal the electric charge of the electron in scalar value for a variety of reasons. One is that the mass of the electron and the proton are 1,836 times different in terms of electron mass. The geometry of the structure of the proton precludes completely any possibility of an equal charge value being expressed if you take absolute charge values. And the charge values that are going to be measured and have been measured indicate a geometric consequence of construction, which involves the golden ratio factor. So I'm now aware that there have now been 3 separate experiments that have been done. One that resulted from my claim because the guys wanted to prove me wrong. One that occurred in the 70s, I think, with my colleague who got weird results. And another one has occurred in China where papers have all been recently published where the Chinese team have claimed empirical evidence of what is said. And further, they are claiming that the actual electric charge of the electron or the proton can actually vary. And if we talk about how the electron construction and proton construction occurs, then such variance should occur. And I find it most gratifying that there's now experimental evidence that these claims that I had made are actually standing up. But there must have been in the last 114 years others who have done experiments along these lines and discovered these anomalies, but due to assumptions and acceptance, Millikan got it right type ideas, the experimenters would have viewed the data as questionable, just like Millikan did. But going back to what Millikan actually did in his experiment, I think that experiment would have detected the positive charge electron and the antimatter electrons. So he didn't just measure, just normal electrons. He would have got the whole deal because of the way matter constructs occur. So if we were to go back and carefully examine Millikan's data and not be so strict in his claim that these values were unreasonable, we might have a different understanding of what he actually measured. So when we look at the textbook and it says the Coulomb value of a proton is minus the electron Coulomb value, well, the textbooks are wrong. So that's what.
The only thing because I haven't studied charges since college, but I will point out that even in college they told us that Benjamin Franklin had assigned them arbitrarily, and everything keeps coming out to negative, so just ignore the negative for the final results. But I will say this, just mytho-historically, the electron must be the positive charge actually, because it's the yang, and the proton would be yin relative to. But what you're suggesting makes a lot of sense to me, in that the proton could have multiple types of charges depending on its arrangements, and essentially the conditions that it exists with the so-called neutrons around it. Why don't you go into that?
Well, the neutron I've been claiming is a hybrid particle, but if you look at the SAM model, they're claiming that the neutron does not exist. So what they're saying is the electron gets sandwiched between protons, providing a glue. And if we understand that a neutron is an electron, a proton, and a photon quantity equal to an electron mass, you get a stable geometry for the electric charges to attract sufficiently well to bind the nucleus. If you go back to Weber's work, he wrote papers in 1846 and 47 where he said if the like charges are close enough to each other, they will actually attract. And this is known as simple electromagnetics, and it's been misdescribed. So if I get 2 like charges, they won't repel necessarily, they can attract. And if the charges are rotating in the opposite direction to each other, they will attract. But if they're rotating in the same direction, they will repel. And if it's unlike charges, if they're rotating in the same direction, they'll attract. But if they're counter-rotating in opposite directions, they will repel. And this is not typically covered correctly in the electromagnetics, even the stuff that's taught in universities. So there are a number of issues to do with electric charges, their values, and the effects thereof. And as a result, we've got textbooks that are not correct, mathematics that, because these charges are actually not scalar equivalents with a sign change, you end up with results in the predictions of what will occur that are not in agreement with what was speculated. And people will fear to tread on that environment because it's pretty fundamental to the way electromagnetics is described. But when we say, oh, Weber's being ignored, who's this Weber guy? Well, you read the second volume of Maxwell's treatise on electromagnetics and you'll find it is just Weber completely from end to end, because Maxwell actually examined what Weber had written. So the reason why I like Weber's electromagnetics is because he treats the electric charges involved as separate. In other words, we don't have one electric charge we assume to be static. We have everything in motion, and you've got to work it out as that. Whereas the Maxwell equations and the Maxwell electrodynamics has one of the electron charges or electric charges as stationary. And the problem I have with that is nothing in the universe is stationary at all. The secondary problem I have is that the geometry of the mathematics is two-dimensional, when the expression of how these particles move in terms of space is three-dimensional. And when you condense three dimension into two dimensions, you wipe out a whole set of interactions that do occur. And the third element that's involved is that Maxwell's equations does not account for fractal charge, which is what NRAF produced in his experiments, nor does it correctly account for motion in three dimensions. And the motion that occurs in three dimensions in the real universe is always a helical path travel. It's never straight line, it's never a circle, never an ellipse, never a parabola or any of those other types of motion paths that are described in simple mechanical motion. So there's some real issues in both the physics and the understanding of what's going on in electromagnetic interactions that are occurring. The final thing over the experiments conducted by both Millikan and NRAF is that the magnetic behavior of electrons and protons was never ever considered. So the experiments have additional wrinkles in them that are not going to show up easily because of the way the experiments have been understood, the assumptions that have been made, and the mathematical model that was used. And yesterday, the last video, I stated that you can make the mathematics work to whatever assumptions you choose. So if we've got the assumptions that I've described as being a problem being glossed over, then the mathematics that supposedly describes what's going on is critically flawed, and you are going to get anomalies. And this is known in electromagnetics, that the Maxwell equations set developed by Oliver Heaviside does not always work in all circumstances. There are times when the equations just simply fail to correlate with what is observed. So that's my spiel. And everybody's gone quiet on me. So when we look at experiments, we've got to ask ourselves the question is, have we really thought them through? I've made a criticism of Ampere's assumption, which is involving that a moving electric charge produces a magnetic field. And I'm saying that photon behavior and a few other factors show that that assumption can't be true because of the way the photon behaves in terms of oscillating electric and magnetic fields that are in step. So that if the field is being counter-generated, when the fields go to zero, which is what's described in places like Wikipedia, the photon should just cease to exist because there's no electric field to continue the magnetic field, and you don't get the continuation from the null point. So the model for the photon and the assumptions between electric and magnetic generation are not what's going on. And although we see in modern claims of this that, you know, the electron's spinning and therefore it's self-generating in a magnetic field and all the rest, it's unproven and it's untestable. That actual configuration idea is untestable. And if you listen to Feynman, something that cannot be tested by experiment has to be wrong, which is where cosmology has some big problems because their ideas can't actually be tested by experiment, which is, you know, the way of science, I suppose. So those experiments, when I started to understand that the Millikan experiment had a problem with it, that Ampere's assumption has problems with it, I then started thinking about the gravitational experiment that was done with the Cavendish experiment, which is two big metal balls and two small metal balls that put on a rod, a silicon rod, and then over a period of 3 days they start to move. And my colleague says that for that experiment to work correctly as it claimed, the steel balls have to weigh 1 million tons, the big ones, which means the experiment that Cavendish did is just not heavy enough, as it were. But I think that there's an actual mistake in the understanding of what's actually occurring. What we've got to remember is that the Earth is rotating on its axis once every 24 hours. And for the balls to start moving, it's 3 days down the track. And when you examine the behavior of angular momentum in that environment, you would expect to see this behavior to occur very slowly over time as angular momentum from the rotation of the Earth actually impacts the experiment itself that's supposedly measuring gravity. So
It's going to be a hard proof for two reasons. One is all the experiments will be done on Earth, and two, the argument against worrying about angular momentum from the Earth is the velocity and energy levels for these particles are considered to be such that the angular momentum is imparted on them is essentially zero. And when I say essentially zero, I mean that it's 10 to the minus, 30 or something like that, where there's just not even a real consideration that it would have an effect. You might be right, but it's probably beyond the physical limits of our atoms to actually, of our machines to actually detect that.
I'll give people another way of understanding what I'm trying to get towards. In the New South Wales University's Physics 101 course, that's the initial course that university graduates engage in before they get their degree, is that there was the lecturer who was doing it used to come in the first lecture, and there's this great huge